Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 16, 2026, about 5 days ago. It introduces an efficient generative framework that can produce high-quality images in a single forward pass, competing with complex diffusion models using fewer than 5 steps. The paper is titled, Image Generation with a Sphere Encoder, and as we'll see later, the implications for fast, high-fidelity generation are really promising. To start things off, Figure 1 presents a gallery of samples generated by the Sphere Encoder across different complexity levels. The top rows show results from the one-step regime on CIFAR 10 and animal faces, demonstrating that a single forward pass can yield coherent structures. Moving down, the model uses just 2 steps for Oxford flowers. The bottom section showcases ImageNet generation in 4 steps, which is particularly impressive because it produces diverse, high-fidelity images at 256 resolution, covering everything from flamingos to baseballs. Well, Figure 2 breaks down the architecture behind this efficiency. The process begins with the encoder, E, which maps an input image onto a global spherical latent space, represented by the blue sphere, S. Crucially, the model learns to distribute these embeddings uniformly across the surface. This means that to generate a new image, the system simply samples a random point from the sphere and passes it through the decoder, labeled D, which reconstructs it into a realistic output. So, Figure 3 contrasts the sphere encoder with standard variational autoencoders to highlight the posterior hole problem. In the top 3 rows, models like Flux and SDVAE reconstruct inputs perfectly in the second column, but fail when generating from random noise in the third column, outputting only static. This happens because their latent spaces are not perfectly aligned. However, looking at the bottom row, the sphere encoder works differently. Because it forces uniform embeddings, sampling a random point directly yields a realistic result, like the cat shown here, without any extra diffusion steps. Moving to the specific mechanism for achieving this uniformity, Figure 4 illustrates the noise injection process used during training. First, the encoder maps an input image, like the baseball on the left, to a precise point V on the latent sphere S. To prevent the model from just memorizing isolated points, the system adds random Gaussian noise, shown by the dashed lines deviating from the center point. The decoder is then forced to reconstruct the original image from these perturbed, noisy locations. This strategy is essential because it smooths the latent space, ensuring that even random points sampled between training examples decode into coherent images. Alright, having seen the training mechanics, Algorithm 1 details the actual generation steps. It begins with the one-step generation phase, where the model samples a random noise vector, maps it to the sphere, and immediately decodes it into pixels. If more detail is needed, the code proceeds to a few-step refinement loop. In this stage, the image is re-encoded and guided, both in latent and pixel space, to iteratively improve quality while keeping the total step count low. So, Table 1 quantifies these generation results on the CIFAR 10 dataset. In the top section for conditional generation without classifier-free guidance, the Sphere L model improves rapidly as steps increase, reaching a generation FID of 1.65 in just 6 steps, which outperforms the StyleGAN 2 baseline. The bottom section is even more revealing for unconditional generation. Here, the Sphere L model achieves a competitive FID of 2.34 in 6 steps. In stark contrast, standard diffusion models like DDPM require 1,000 to 4,000 steps to achieve comparable quality, highlighting the massive efficiency gain. Well, Table 3 scales this evaluation up to ImageNet at 256 resolution. The middle section lists diffusion baselines like ADMG and SID, which typically require hundreds or even thousands of sampling steps. Down at the bottom, however, the Sphere XL model achieves a competitive generation FID of 4.02 in only 4 steps. This performance surpasses the standard ADMG model, which needs 250 steps to reach a higher FID of 4.59, proving that the Sphere encoder offers a massive reduction in computational cost. Wrapping up, 2 takeaways stand out. First, the Sphere encoder shows that high-fidelity generation doesn't require thousands of diffusion steps, often succeeding in just 1 to 4 passes. Second, by enforcing a uniform spherical latent space, it solves the posterior hole problem that limits traditional autoencoders. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.